I love it.
Yeah, actually, might get this job.
Okay, guys, I think we're ready to start. So we have a special guest today, Fru's in the back, who you all should know by now, and also going to give feedback on this class and teaching, and I've gotten some more feedback from you guys, so thank you so very much. We are going dark. What happened? Come on back. So I'm going to review just the midterm answers, and then we're going to get into deep learning today. And you guys started off the class okay, cool. Okay, so you guys started off the class by by using observations of species to then predict distributions. And in that case, the response variable is just presence or absence. So it's like the simplest form, a 0 or a 1. So that's a classification, right? It's a 0 or a 1. And in this case, the classification that you guys are going to be chewing on is going to be what species is it? But now we're going to be using very complex input data, which is going to be imagery. But you can also use sounds. You can use really complex input data, which is what deep learning is especially good at. When you have a lot of data and it's more complex in nature, to then be able to do the prediction and get something back that is the original objective. So we're going to go into the deep learning and talk about neural networks. But first, thank you for using the feedback form under the course schedule heading. And there was one comment about, like, it doesn't seem very fair that you changed the question and now we might have answered it already. I'll accept either answer. I just wanted, for clarity, when I changed the question, I included what was previously there. So you had a heads up about like what changed. And it was really meant to just elaborate like more understanding. So if we go back and look at this ordination lab, for instance, one of these questions was just kind of hard to read. So the idea was just to, and this came up in Slack of like, oh wait, how do we read this ordination surf function? So in the question, I went from a very simple question that was a little bit difficult to interpret to more explanation. So if you responded to either, that's sufficient. It's more just like, okay, that question should have been worded better. So don't feel compelled. It's more just for clarification, but also to give a heads up about what was there and what's been changed. And along those same lines, there was also a really valid point about explanatory text. So I tried as much as possible to pull in reference materials, But in some cases, that reference material was really opaque, very difficult to read, like with the ordination vegan tutorial. So I did go back and added, you know, the explanatory text that was like my interpretation that's more readable. But I did that after the fact from the original post. So I made that italics. So that's also something that I will go back to do with the others, and that I will continue to do as we're borrowing materials like from this deep learning book, and then I'm peppering in some comments in italics so you can differentiate the two. And then also along those lines, there in the main course page, I realized that you know, in subsequent labs, I basically said, okay, go to this exact section and hands-on with machine learning with R. But in the earlier labs, I just said, okay, we're going to use this source material, and I wasn't as explicit about what the code corresponded to. So I updated the the course schedule to reflect the actual sections of the different things that I was referring to. And then I'll go back and add more of those explanatory texts for well, mostly for next year, but you guys for your own understanding this year too. And I linked these more explicitly, but the textbook references are italicized, just because, you know, if we're going through chapters, we don't need to repeat the whole name. And then the articles are just author year. And so that's also reflected down here in the readings. And then the links are to either the online book and hands-on machine learning with R, or to the PDF, which is in the UCSB folder. So you need the UCSB login to get to, so we don't infringe on copyright. So yeah, so we're learning as we go. We're learning about how to teach machine learning, and hopefully this is more explicit and more useful should you need to also go back and reference this material. Okay. And then I think we'll just go over some midterm exam since you guys took that last time. And I'll just do a preview and we can just walk through some of these. Okay. Okay, so the most common type of machine learning is, what it'll be? I'll just have you guys call out the answers. Yeah. Supervised learning is when a model fitted from both predictor and response terms, whereas there's an extra whereas with what? Model is not fed an explicit response term. Blank. Semi-supervised learning, but supplements by amending the model fitting with user feedback. What now? Sets up a game-like environment to learn through experience with penalty and reward. Okay. RSC and AUC are example outputs of this process. Evaluate. Separation and training and test subdatasets. Split. Model training. Predict. Use of new data. Whoops. Oop, that's predict. Model training. Process is fit. Yep. Okay, the superset of blank is broadly the ability of machines to perform tasks previously thought to require human brain power. AI. Then the superset is blank. Machine learning. The ability of machines to learn patterns from data. A further subset is deep learning. Cool. Species distribution modeling goes from geographical to environmental space and back to geographical. It's generally the process of extracting environmental data from locations where species have been observed and possibly not observed. Then fitting this data in environmental space. Finally, the fitted model is used to predict across the landscape or seascape to describe. Is this true, false, or partially? True.
I have a problem with this one.
Please. Yeah.
In the ebook and Leeswick paper, they explicitly say like that it doesn't have to be like environmental, like you don't have to bring environmental variables into it at all. It could just be geographic.
Ah,
And so when I read it, if I had read it initially and it was only true or false, I would have hit true and moved on. But
yeah.
because there was partially true, then you like stop and think about it and be like, well, you don't need environmental variables.
Okay. Okay. Yeah.
So
Okay. So I'll accept that. There's always like some very, fine shaving of terminology here. And in this case, yeah.
Yeah, from the paper it says the ecological roots of SDM belong in those early studies that describe biological patterns in terms of their relationship with geographical and or environmental patterns.
Yeah, that's fair. Yeah.
If it was only true or false, I would have hit true because I think that it's maybe more specific, making it kind of partially true.
Yeah. So also just to add to that differentiation. So there's a whole branch of like geostatistics, which is interpolating things like inverse distance weighting or kriging, and that's using just the geographical locations. So then kind of predict. And actually, the guy who the fundamental principle of that is like it's named after a Tobler who was at the geography department at UCSB, and which is he just basically explicitly stated things that are nearby tend to be more related than things that are far away, and so that's the premise of that. So yeah, so that's why if it's just geographical, then I wouldn't consider that personally. Like I would consider that more like geostatistical modeling, not species distribution. But because you quoted so aptly directly from the paper, I'm totally with you. So yeah, okay, that's absolutely fair. Okay, so true and partially true will be accepted. And feel free to shout out if you have any other objections on these things. Okay, match the modeling method, branching method to divide the predictor variable space. Yep, multivariate regression modeling that fits simple coefficients, GLM, and multivariate regression modeling that fits more complex coefficients, additive. Okay, a true observed absence of a species is associated with systematic surveys. And in the lab, you use presence only data from GBIF. You generate pseudo absences by circumscribing a polygon around the points, i.e. a convex hole for containing the random points function. The blank modeling method is different from other logistic regression methods in that it automatically samples a set of quote background points for you. So, accent, cool. Okay, logistic regression constrains the response from 0 to 1, applies a logic transformation of the response, and is used with input data that has a binary response.
I have a question.
Yeah.
Why is C true when we've done like logistic regressions that have more than like categorical variables?
So the logistic regression, that logistic part is actually referring to the logit function. So when we went over that, and that's what constrains it from 0 to 1. So when we talked about logistic regression, this is linear regression where the values can range outside of 0 and 1. And then this is logistic regression. And that's where there's two possible values. And so it's binary, one or the other. And then this is the actual, you take basically the log in this odds probability on the response term, and that's what then constrains it to going from 0 to 1. So logit is like this weird thing where it's using the regression techniques, which are more generally speaking used on a continuous response term, but then applying this logit transformation so that it's like a classification response. So it's like a funny little hybrid because of this logit transformation, and that's the logistic and logit. I don't know, some funky word play there, but it is granted a little confusing. And somebody pointed out, like, well, it could actually be not just binary, but multiple classifications. And technically, that's actually true. But that's just using the same tool and then just creating binary responses for any classifier that you add on the other end. So it's really just the same. But yeah, logistic regression is true in all these cases. Does that make sense? Yeah. Cool. Yeah.
So I was reading C as like the data that we're putting in is already in a 0 and 1. It's already in a binary response. So the fact that we're like constraining it to 0 and 1, that's not how I read that. So I was just kind of wondering if you could explain how, like, is the regression that we're doing, is that considering after you constrain it, or is the regression actually constraining it, and that input data that we're putting in isn't 0 or 1, but we're like constraining it to it? So can you clarify that? And like, I think that was, I don't know if anybody else did it that way. Yeah. Okay,
Yeah.
cool. So I guess that was kind of confusion on how it was worded. But if you could also explain that.
Yeah. So I was realizing that by the time we got to the evaluation stuff, that we need a more clear understanding what is predictor. So what's the X on when we look at this model? You've got your predictors, your X's, and then you've got your response, your Y's. So this is the data that's going in, and these are your X's, your predictors, in a table. And this is your Y, your response. So this response that you're fitting or training the model on is already just 0 or 1, its presence or absence. When we do the modeling, some connections there, we go. When we fit the model, the model can then predict a continuous range from 0 to 1. But then, so we can get this range here of prediction, and then it only gets converted from that continuous range from 0 to 1 to a binary, an actual 0 or 1, similar to the original input when we apply that threshold that's based on that ROC curve, and then we can get that. So the question is actually meant to, like, all the terms are actually really important. The input data of the response is binary. So the input of the predictors is continuous. It's an outside of 0 and 1. But the input of the response is only 0 or 1. So it's binary. So that is consistent with the question, but it is confusing that the model can predict a range, and then we only recover that final 0 or 1 when we apply the threshold. And then once we apply the threshold, then we get that confusion matrix that allows us to say, like, how well did we predict the 0s and the 1s? Is that cool? Okay, I'm seeing some head nods in the proper direction, which is great. Okay. So this is E all the above. And then multicollinearity is the problem with multiple input predictors being autocorrelated with each other, which can lead to misinterpretation of the supposed to be relationship between predictors and response, i.e. a positive coefficient fitting a model with a single predictor x1 can become negative if it's autocorrelated with predictor x2. A blank can be calculated between any two predictors. Yep. These pairwise calculations are often visualized with a pairs plot, perfect, that Also shows a scatter plot of the two variables. The blank can be calculated to show which predictors contribute the most. EIF. Yeah. Okay, cool. So which of the following are true about term plots? Show the relationship between predictor and response. Can be scaled on the y-axis to the response either before, so varying beyond 0 and 1, or after the Logit transformation, depending on the modeled method and term plot function used. Have dashed lines can be plotted to show the standard error around the average response, and a response in which the dashed lines span the y value of 0 is considered to not be statistically significant. So that was a lot, but yeah, it's all of the above. And this is where, like, yeah, I should have had more explanatory text to explain all that, all those aspects, rather than just. What D means? Yeah. So if we look at, like, especially like the GAM term plots, so this is where, like, this is the 0 on the Y, and the over this, basically through here until we get to over here, the dashed lines are spanning the value of 0, meaning that it's not, this is within the range of error. It's not statistically significant, this influence of this variable on presence or absence, until the axis is here. So it's a very visual thing that is difficult to understand from the text alone, but where this line goes through, the statistically significant contribution of this variable to the response, so presence or absence, needs to be outside that line. Yeah.
I guess my understanding from doing this lab is that when the lines are closer together, it means that you're more confident, right? And
That
so
is true.
That it doesn't have to do with the dashed line spanning 0, but it's the solid line spanning 0.
From our discussions with
So like where the dashed lines are exactly is less important than if the solid line is going along 0, then that means that we don't know what's going on. Like we can't really predict what's what. But the dashed lines being there, they're there because that's where the solid line is.
So
That's what confused me about
there's two aspects in this. One is what is the average of what that term, that predictor is predicting as far as presence or absence, and then the other is what's the confidence about it. And where we, this is also the rugosity part, or the rug plot, that shows us where the observations are that allowed us to fit this relationship. And generally, where you see very few observations, you get these very wide tails. So even though the average seems to have like the greatest effect on this outer value, we also get the most variation, uncertainty. So when we say like something is statistically significant, it's not only has an effect, but we have it with certainty. So that means that there's the solid average response is both inflecting outside of 0, and it's with the statistical confidence that we have about that is within a range that also deviates from 0. And that's why that line is kind of to be viewed. And it's too bad that this term plot doesn't actually plot the line. Other functions, other modeling methods automatically have that. But yeah, like here, it deviates. Where they say, you should be really careful with extrapolation, especially if you're looking at things like climate change. because the original data that you have that used to fit the model might have very little information on the outer edges of this environmental space. So if we're looking at temperature, we might only have a few really hot points of data with really extreme temperature, but then we could be extrapolating. And typically when you're outputting these maps, you're looking at the average response and you're not looking at the uncertainty. So it's just, that's why it's good to keep this in mind, is that it's the average response, the solid line, plus the amount of confidence we have about that response, the dashed line.
I just want to ask you another clarifying question. So according to what, how are we supposed to know what is significantly significant? So according to the p-values, this feature, if you will, is significant.
Yeah.
So can you show me one that's not significant? And then, which on this slide I think is topo wet and ER try.
Yeah, so ER try and topo wet. So
Just looking at the looking at those graphs, which is how I
exactly. Perfect. So this is the better example of what I was just talking about. Thank you for pointing that out. Because this ER try, so it's kind of both cases. So yeah, I mean there is a little difference from 0, but the entirety of this response has the dashed lines, the confidence that spans this 0 axis. So at no point is it helping you determine the presence or absence of the species along its entire gradient. So it's non-significant. So this is, yeah. And the same you could say is true with ER topo wet, because we don't have the little asterisks with the p-values of less than 0.05. And so you'd also get you get a little bit more wiggle, but it's even less significant because it's quite broad. So 0 axes, the dashed lines always span, both dashed lines span that 0 axis. Yeah.
So the dashed line, in order to make the entire figure not significant, the dashed line, the entire length of the graph have to encompass 0. And if at any point the dashed lines both go above or below 0, then some part of the graph is significant. So the entire figure is represented as significant. Table with output.
Basically, yeah. Yeah, that's a good way of thinking about the correspondence between the term plot and then this summarized table about which ones are statistically significant. Yeah. Cool. Okay. I definitely want to move on to deep learning. It's kind of a deep topic. So how about, okay, we're almost done. So decision tree methods apply the technique to divide the predictor variable space visualized with a tree having branches and leaf nodes. The blank process, pruning process, trims the tree with the most parsimonious number of branches based on the complexity parameter, which penalizes extra branches that resolve differences in the response training. Relative contribution of predictors to the fitted model can be visualized with variable importance plots, and random forest takes an ensemble fitting approach to many trees. Cluster array is an unsupervised learning technique. The blank approach requires a specified number of clusters, k-means, visualized with a Baroni diagram. Whereas blank allows for a non-specific number of clusters, hierarchical clustering, and can be visualized with a dendrogram. Cool. So ecological distance, comparing sites, can be calculated, such as with Pythagorean, using Euclidean. A similar computational approach based on city blocks is Manhattan, and the most common approach in ecology is Bray-Curtis, for ranging it from 0 to 1 for similarity and dissimilarity. Ordination and unsupervised learning is technique to reduce the dimensionality of the variables in between observations. In ecology, blank ordination refers to those variables only being species. whoops, unconstrained, yeah. Whereas blank ordination, so constrained, and uses species and environment. After ordinating on species, the environment can be overlaid with blue vectors indicating the environmental gradient and or more refined surface gradient and contours fitted with a YAM. Conservation planning reserves are typically designed as an optimization problem to minimize the cost of planning units, penalties on target features that are typically species or habitats, and blank to clump for easier management. Boundary line. Awesome. Okay. So thank you for the clarification on, there's a couple points that I think were a little fuzzy, and yeah, I'll take that into mind when I go back and add some more of that explanatory text. So let's get back into actual deep learning, which is a really fun topic. This is from a slide from the intro, where it's like deep learning for imagery or sound. And again, this is like, it's fairly complex input data. And in this case, maybe we're predicting a species. Maybe we're predicting like where that species is in the image. And maybe we're actually like doing what's called image segmentation, where we're saying pixel by pixel, here's the outline of the species. Or if you're looking at sound, then maybe what the species is, like what range it's actually vocalizing over within the spectrogram. So there's a visualization of sound where it's time on the x-axis usually, intensity, color, and then y-axis is octave. So high and low pitch. And then yeah, more sound stuff. So deep learning is really applicable in ecology. This is just from individuals to ecosystems. And for the lab, what you guys are going to be doing is working on a subset of this iNaturalist. So if you haven't tried out this app, I highly recommend it. So cool. You just basically take a picture of any living thing and it does a fairly decent job telling you what it is. So Scott Laurie, who co-founded it and is a buddy from Duke days, he's going to join our expert discussion at the end. And you guys are going to be similar to the species distribution lab, where everybody had a different species. You guys are all going to be given different comparative species subsets of this. It's actually like, I don't know, 200 gigs, the whole thing. There's a lot of imagery here. And this is also a Kaggle. So this is how so much is learned, is through competitions. And then there's cash prizes in some case, jobs. So it's quite cool, and this is an ongoing thing. So we took a little poll. You guys want to, I had originally suggested we switch over to Python. Do you want to use R or Python? It was actually pretty much split down the middle. And so I really enjoyed this deep learning with R book. It's like, it's so refreshingly readable compared to some of the stuff I've foisted on you guys. And it turns out that yeah, the same author that did this with J.J. Allaire, who's the founder of RStudio, he actually had a preceding book just before it called Deep Learning with Python. So you can choose your own adventure. I love these books as a kid. It's like not of your generation, but yeah, it's you basically could like get to an end of a chapter and then you make a decision and then you go to a different chapter. And so you guys are going to basically do that. You can pick up either text, and what's amazing is that it's actually the same, almost verbatim, the same text and the same figures, just the code is different. So either one will do. There is a 2021 second edition, but I'm offering you guys the 2018 version that is like a mirror copy of the R version, so that we kind of stay in sync and the concepts are the same. It's just slightly newer techniques in 2021. There's a couple of videos that I just want to point out here too. One is what I saw 4 years ago at the RStudio conference by J.J. Allaire. It's an hour long, but it is gold. He does a great job. Also caveating, you know, there are limits to this. There's a lot of hype around this stuff, and understanding where it is and isn't applicable. And then this was just a couple weeks ago. Jeff Dean, he's been at Google for 20 years, which is basically as long as Google has been around. I think he was like employee number 4 or something. And he's like a god in the space. He's the head of Google Brain, and the TensorFlow that we're going to do is going over this. This is also extremely approachable, 18 minutes, where he talks about in very simple terms what this is, and then like what is the future, where we're going with it. So I'll leave that for your viewing enjoyment. So we've seen this basic figure before. We just reviewed it in the midterm. You know, AI is the superset and deep learning is the subset with machine learning, kind of in between. I like his definitions. I heard from Jamie that some of you are like very interested in being able to explain stuff, say in a job interview. So having, you know, spot on, you know, recall about like how these things are differentiated, I think is good. And so I'm offering the page numbers here. So AI is intellectual tasks performed by humans. Machine learning, I kind of like his wording here, where it's useful representations. It's kind of like we're taking all that input and then we're re-representing as, oh, is the species present or absent based on all this environmental data, or you know, is this, what species is this image I'm looking to, then something very simple that is useful for whatever management or you're doing. And then deep learning is really a subset of machine learning where we're using this special structured technique of just adding layers. And the actual math behind it is you had in high school pretty much, with a little bit of linear algebra specifics. It's actually fairly simple math. The trick is that how it layers this content. And you know, originally machine learning like talks about how you could play chess and they could come up with rules to beat the average person, and eventually they came up with programming rules to even beat a world grand champion. But it took a lot longer to beat the world champion of Go, because it's a much more complex game. And machine learning part is the machine learns the rules to then apply to figure out how to win, or apply to figure out what the objective is. And so this is an example used to talk about how things can be transformed into something that's more interpretable. And in this deep learning kind of space, these are the predictors are also called features. And now this coordinate transformation, you can see that the white circles get everything negative x, and then black circles positive x. So that's a useful coordinate transformation. And there's a whole field of like feature engineering to basically take your inputs and then make them easily interpretable to get new rules to come up with your output predictions that you want. And this is a classic example. This is like hello world of deep learning called MNIST. And so this is what you guys are going to do today is take this data set. And one of the early examples he talks about is the US Postal Service trying to figure out where is the zip code on a letter and automatically sort it. So they had a whole bunch of handwritten and different versions of numbers. And this was the big task, was like, how can we automate the sorting of all this mail? And so this MNIST data set was one of the early examples of it being useful in the real world. And so think of, you know, each of those numbers could also be a species, and you're trying to figure out what species it is. And you have this original input, which is an image, and then you get this final output, which is just a classification, like, what is it? Of these 10 possibilities, which one is it? So that goes back to the transformation that happens at each layer. So each of these layers get stacked. You define the layers, and it does some new transformation. And then you start with some initial conditions, and then use this back propagation method. We'll look into this more, and some gradient stochastic descent stuff. And then with each layer that you define and how it transforms it, you then get the same output. So the trick is in understanding how to do the layers. And then the magic of it is the fact that you don't have to tell it the rules. It will learn how to adjust the weights for each of these layers based on the inputs. So I like this, a multi-stage information distillation operation. That was fun. Yeah. So with each of those layers, you've got these weights, and the learning process is just figuring out how to assign those weights differently and parameterize them. And then in the end, so similar to what we talked about when we were talking about evaluating the model, we have a loss function, and that loss function, we're trying to reduce it, or it's an objective function, and it will then rejigger the weights and keep going until we get the lowest loss function. So the objective is a lower loss score, and there's some optimizing engine based on how we set up this neural network, and it uses this back propagation algorithm over a training loop. So initial values are assigned to the weights, and then it applies those and says, like, okay, here's what we predict versus here's what we know is true. So we have that training data that's going in, just like we talked about before. And we're going to look at that difference, and we're going to keep on trying new weights until we reduce that difference. So other terminology that is used here is, okay, so there's a classification problem in each category. So we have a 0 class, a 2 class, 4 class, 3 class. You could have different species for each of these classes. It's basically whatever is the class. And next time we'll talk, actually, we'll go into my, okay. Okay. So the data points are called samples, and then a specific sample is a label. So imagine you've got a table of images. Each cell is an image, and then it has a label, and that's your input data. And in this case, there are these grayscale handwritten images, so 28 by 28 pixels, and they have 10 categories, so 0 through 9. And we'll talk about this as a quote tensor in a minute. So the idea is you feed the neural network. You do the split. You have the training and you have the test, and then you've got the images, which are the like just like the X's, the predictors, and then you've got the labels, which are like the Y, the response that you're looking for at the end. And you're just running it through this layered model, and it then applies all these weights and tries to get the label response back out. And then you confirm that it came up with a reasonable answer with this independent test data set of images and labels. Okay. So
Are we telling it how many layers to do, or is it?
yes. So we're going to get into a lot more of the specifics about the architectures of these things with the layers, but exactly. We're going to start off with this simple example, and we're just going to use 2 layers. And we're not going to dive too deep into all of the nitty-gritty until next week. I just want to show you how simply it can actually be done. There is a slight annoyance where, for some reason, you have to have a locally installed version of your Python and the library on top. So basically this, even though your R on Taylor has these packages, really in R, so I'm just showing the R example and I'm going to show you how to load it up in Python. And in R, they basically came up with this reticulate package. So Python, it's like, actually it's, I guess JJ Allaire likes reticulated Python. So you just want to name it after a Python. It doesn't really matter. And even Python, you guys probably know. Guido von Rossum named it after Monty Python because he thought they were hilarious. Not even the snake. So anyway, this package is what translates objects from R into Python and then gets them back into R. And so that was specifically developed to enable the use of all this deep learning. So it's like directly analogous. The code in Python is very similar. There's some specifics about using NumPy, which is the like a tibble or a data frame in Python, but it's very similar. So you just need to install Miniconda, which is a small version of Anaconda, which is a Python distribution, and then Keras. So there's TensorFlow, which we'll talk about in a minute, and then Keras. And Keras is like the orchestration layer, the orchestration package that communicates with TensorFlow. And then you just need to point it at that version once you install it. And then you can also do code chunks in R Markdown. So you can continue to use R Markdown, or you can load this up in a Jupyter notebook. So if you go into Taylor, so you can create a new RStudio session or a Jupyter Lab or a Jupyter Notebook. Jupyter Lab is just a little newer, so I recommend that one. And then if it's a Jupyter Lab session, so this is the Python version. And so I already have this, but in the Jupyter, you'd want to select Python 3 kernel to just launch a freshie, or so there's a GitHub repo with this deep learning with Python and the code base and all the notebooks in it. But it's not a different one for the 2018 version. So this is going back to a specific commit. So you see the commit here before it got updated in 2021 to the second edition. So we want to use this older edition, and you can just you can download this notebook, and so now it's a locally available IPython notebook. And GitHub is kind of nice with these IPython notebooks because IPython notebooks actually under the hood are it's just like this JSON document that stores the text and then the outputs and then the cells. So now we can just upload this thing. Oh, I've got a whole folder there of it. And sure, I'll overwrite that one. And then you can open this file once you've downloaded it, and you can just start hitting play. So you guys have used these Jupyter notebooks already. So this other message here is related to the hardware. So we have CPUs, that's the main computer central processing unit in a computer. When they report speeds on like how fast your laptop is, that's the CPU. But then we have a graphics card, and that's the GPU, the graphical processing unit. And there's a major innovation. The book talks about this history where NVIDIA, like they basically realized for these deep learning operations, which are basically just a whole bunch of linear algebra equations that you can run simultaneously, that's what a GPU is actually designed to do. Is it's like doing ray shading, and it's just doing a whole bunch of small little mathy things. And then they came up with this. NVIDIA came up with an interface programming library called CUDA. I don't even know what it stands for, but and all of these deep learning tools take advantage of your graphics card. So if you're really serious about getting into this, then you'd want a beefy graphics card and use CUDA and send it all through that. So this error message is basically saying like, whoa, you don't have a GPU setup. I don't see CUDA. What's up? I want CUDA. I don't have it, but it's okay because I'll just use your CPU and you'll just be like a slug crunching this stuff, but you can get through it. So for these smaller examples, this works fine, but that's the error. And you'll see there might be other error messages that you get similar to that. So, and then you can just chunk through, and you can also, insert, and you can insert a new cell, and then you can change that into like a markdown cell, but you guys have used these before. And then, yeah, you work through it that way. So I want to let you guys try this out. So I'm just going to talk through a little bit more of this, and then make sure that you guys can actually run this with a few minutes left.
Can you go back to where you downloaded it from? Which one are we downloading?
So if this whole lab is set up as a choose your own adventure, and we're playing with numbers, we're using the MNIST data set, and there's a section 2.1 of R. So I'm sharing the R code because it's the simplest transferable. And then if you want to use Python, you can go to that section where it says Python. And then in that section, I have a link to that GitHub repo. And then you can even just right click and save link as locally directly from this notebook here. And then upload to a new Jupyter Lab session, Python 3 notebook, and proceed to check through the code there. So, yeah.
Maybe I just need to rename it, but when I try and open it, it says readable notebook.
I wonder if did you save this link or no?
I clicked it and I kind of went to that first notebook.
Let's see what this. Oh, page not found.
If you
Huh.
click the first link, it goes.
Yeah. So you did this,
And I just downloaded that one.
and if you said save link here, that is I think, yeah, that is saving not the content. What? Exactly. Yeah. So this is, if you save that, that's saving the GitHub page. That is the wrapper around the content of the notebook. And that's why I say here, if you want to go that route, then shoot, where to go? So here I'm saying similarly, so go to the GitHub folder, and then on the raw, click on the raw, save link as, and then that's the actual content of it. So if I click raw, you'll see now this is the raw version, and this is a JavaScript object notation. So it's just a way of having any kind of defined stuff. So it's an array with something called cells, and then that's a list, and then so it's a dictionary, and then within that it's called cells, and then you've got a list of the cells, what their cell types are, and what their content is, and et cetera, et cetera. So this is the raw version of the notebook as an IPython notebook, and you want to, if I'm in this, I could do file save page as, and that would also suffice. So yeah, it's a little confusing, but you guys can sort that. But if you crack it open in a text editor, this is what you should see. Is something that looks like this. Okay, cool. So I just want to go back to a few slides here. So this book does such a glorious job describing really some tricky stuff. So with tensors, you're using a package called TensorFlow. What's a tensor? What's going on? So the flow is just like you've got these layers and it's flowing these weights one layer to the next. And a tensor is just a way. It's just a generalized data structure that for a multi-dimensional array. So you can have a 0 dimension, 1 dimension as a vector, 2 dimension as a matrix, 3 dimension as an array. That's the R specific speak. And each tensor has a shape. So in R, you'd use dim. In Python, you'd use numpy array, and it's object oriented. So you'd say dot shape, and then it would tell you like what the shape of it is, and then how many axes. So that would be the length of those dimensions, or the ndim in Python. And then what's the data type? So is that integer or floating point, character, what have you. And then you can have all kinds of dimensions. So a dimension could be a time step, could be features, and then the samples within, or it could be like this is an image, it's 4D. So this extra, like you think of an image, it's got height and width, but then there's color channels. So red, green, and blue. So each of these 3 layered cubes would be an image. So you have a tensor of your input imagery, your test or your train images, for instance, in the lab. And then in the lab's case, like even a black and white, that's actually only 1 layer, but because imagery is so specifically expected to have a 4D tensor, they keep that, even though it's a 1 dimension, you could collapse it to a 3D. So something interesting. And then this is speaking to the map, the linear algebra. So these things, there's just a whole bunch of multiplication to go from layer to layer, and then to understand the weights. And this is the actual code that is run in this. And then we're going to talk about this more next week, about these little activation functions. But you can do geometric interpretations. And then this is a fun example of just imagine your data is just like this crumpled piece of paper, and you're uncrumpling it into figuring out like useful information that can be easily summarized into your response of interest. So you guys know what a derivative is. And this is significant because this is the underlying machinery behind how it loops through and tries to assign different weights. So that optimizing engine, there's this idea of a stochastic gradient descent. So we're trying to reduce the loss with each loop. And you can imagine that the loss could actually have, depending on the weights applied, can actually have a weird shape with each iteration and change of the value. And so that's like a local minimum, and it's a multi-dimensional space. And you can have you can hit a local minimum, but there's this idea you want to try to find the global minimum. So it's a whole science unto itself, and we'll dive in more next week. But by changing, it's like how much do you change the weights to then get into this global minimum, versus thinking that you found the global minimum, but you're actually just stuck in a local one. So yeah, that was basically it. But yeah, and then you also notice as you go run this, like here's the actual fitting step where we take the training images. So this is our inputs. This is what we want to train it on to get this output going through the layers. And we have these epochs. So, and then you'll actually see this in RStudio at least. You'll see these dots populate as we're reducing that loss. So we're getting closer and closer to the prediction, matching the training label of interest. And then the actual layers, back to that other question. So network gets defined up here. So this is a sequential model. So we have a dense layer, and we'll talk about what these mean. these activation states. And it's a 2-layer model. And then you say, okay, compile, here's the optimizer engine, here's the loss function or objective function that we're going to use, and keep track also of accuracy, not just loss. So we can see that over time too. So this is how much better as the weights get jiggered, this is how much better the model is doing. So we're getting pretty close to 100% accuracy. All right. So I just want to make sure that you guys can install this stuff and make sure you can run it. So let's, and then we can, I'm happy to take questions meanwhile, but we'll pick this back up next week with more examples. Yeah.
Clarify, the graphs that were like curving, you were talking about the minimums.
Yeah.
Part of featureization.
This is part of the loop that, let's see. So it's this part. So we have an optimizer engine and it uses this stochastic gradient descent. So the parameter space is what it's basically crawling around. Like what's the whole possibility of weights to apply? And then in the end, we want those weights to predict the output. So it should predict 1 of 10 classes of integer with these images. So it's crawling that space of weights and it's trying to find like, where do I go next? So this is some random initial condition of some like theoretical space of weights. And the coloring is akin to your loss function. And you're basically trying to apply weights and you get a different loss value and a different set of weights and you get another loss value. And you're trying to get to a point where you actually find this global minimum. And that's where some of it's like, it's not just, there's a little bit of trickery in getting to that global minimum. Because you could just say, just use a gradient descent, just keep on finding the least loss function when I hit the lowest value, and then it starts increasing by changing the weights again. Okay, boom, I'm done. But you could be stuck in this local minimum. So there's some extra tricks about basically jiggering the weights enough so that you can pop out of that local minimum, get to this other one based on how that descent operates. It's a tricky concept and we'll just have to dig in, hopefully with some more examples next week. But yeah, it's basically the loss that is your final like understanding of how close to your how close is your prediction to the input truth of the image label, and how do we find the absolute best, like the least loss by jiggering weights along the way. So the stochastic part is saying, I'm going to randomly jigger the weights. And the gradient descent part is saying, I want to jigger the weights in a direction that is reducing that loss. Yeah. Cool.
Taylor, like when I'm trying to run, like I cannot import 2 categorical from chat. And I'm going to big red one up here.
I think that some of that's actually okay. So you'll get more like CUDA errors. It says CUDA or NVIDIA. That's actually okay. Let me see if
This one's not okay.
let's see if I can.
That one.
Ah.
Yes.
Huh. Oh, I just did this too.
I know, I also.
How did?
Do it with it's just terminal. And then not.
Huh. Let's see if which
Because we're adding
hmm,
and then we're making a repo.
Make the repo first.
Yeah, so I did. I
And
forgot how
then
to
get
get clone. Oh, yeah. See you. So I want to go into the
hmm.
and so okay, so I'm in it and I have my notebook. And now I get clone.
Huh. Actually, I don't remember. I'm thinking I got the wrong version of the notebook.
Are you saying? She already has everything. Is it in a folder?
Yeah.
You might have to move it, because the repo that you're gonna make is gonna create its own.
So you probably just yeah.
Yeah, you can move it after.
Yeah.
Yeah,
And
the URL.
I don't know.
I know, because I was like, oh, no,
Yeah, we do.
yeah.
Well,
Wow.
well, you have to clone your repo into your, like, wherever you're doing your output. So we had to do it for Tom Stevens' class, even though we were in Git class, because we were on the class. Because I remember
Oh,
asking
I just never
about
did
it.
it.
Yeah,
I
but
didn't-
Taylor, yeah, you just have to SSH and then like, and then,
SSH in every time.
yeah. Yeah. And like to move stuff around, you have to open files up and stuff.
That's
all.
much better. I don't know why I'm doing it.
Well, you have to do it, you have to get clone in your terminal
No, I know, but not have it, but I have it really. I have to do this.
to move stuff.
Yeah. Wow. Jeez. I think we that really fucked us up. We were trying to figure out what. Yeah. None of us makes sense of like instructions. Yeah. It's like clicking around all the different awards. They have instructional and stuff.
Oh, that's why.
Oh, I have my doctorate degree. Yep. Are you doing Oh, I do my. This is supposed to be up here.
Oh, thanks.
Yeah.
Thank you. I think I have to play with. I think there's a version difference. Because it's not finding that function that is in a newer version. So, and I don't know how that changed because I did it. Huh. So weird.
I'm not sure if this,
Oh, yeah, sorry.
I guess I have an issue with the next step now, but
Oh, yeah.
Taylor's yeah. Oh, I just looked up what someone else,
It didn't work.
well, it's working, but I'm getting an issue on the next step, so I don't know if it's.
Cybersecurity is out of control.
Compatible.
I don't know.
Yeah.
But it makes sense that you would have to do TensorFlow dot chars.
Yeah, just add TensorFlow.
I'll see if I get that. Yeah.
Oh, yeah.
We actually said that he's considering, we asked him earlier, because our project.
Ben. Or
Yeah.
It's one or the other. My brain is blanking on this one.
it does.
Good one. Yeah, curious is a subgroup. Okay, cool. Huh, that's so weird.
Then I get an error on the next step.
Oh, okay. But that's cool that you figured that one out. Huh. So from TensorFlow.
And it should show up.
Okay, that was it. Cool.
Mine is also doing this right now. Okay, that one.
Mine actually doesn't run though. It's funny that yours does.
Mine
Okay, that worked. You figured it out. Wait, what? Okay, so on cell 13, I'll just add this to Slack for now.
Are you doing it?
It's just
Fourth time I've restarted.
Yeah.
Wait, that's
That's
so.
amazing.
Yeah.
Yeah, so just say that I have seen that it's like the last part of the I created that.
That works for me.
Yeah,
you-
no, I restarted the kernel and it worked.
Okay, cool. Yeah, good find. Yeah. So Keras is like a submodule in the TensorFlow Python. Module is like generally what they would call an R package or library. So we just need to prefix that and then back in business. Good find. Yep. Uh-huh. Oh. Oh. So I ran the text.
Wow. Wait, you need the R.
Ah, thank you. Funky.
What's your command line?
So I guess can you go which buy this is?
I want to go one.
Yeah, I guess
This.
I don't know if there's a.
Oh, 12. It is 12. Around cell 12.
Oh, yeah.
So I think what I'll do is I'll change the I'll just fork this notebook. And sure. Yeah.
So I did.
No. Get at. You can always do get status. Me too. I just like I already know it's
Yeah.
well.
Does that work?
Oh.
Yeah, it's fine.
Oh.
No.
Thumbs up.
The reason I just want to encourage salaries is because I know it's installed and run into problems. So I just want to say like, yeah, these are Put on Taylor. and-
No.
It's been a long time, but it's been a while.
I, you know what I did while last quarter? I did have a desktop.
Yeah, I guess.
Yeah, we'll get you. Yeah, not your doc. Yeah.